Hello students, today we are going to discuss about the topic buffer capacity and buffer equation. Buffer equations also known as Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. Buffer capacity, first topic, buffer capacity. It is defined as the amount of acid or base that must be added to the buffer to produce a unit change of pH. That's known as buffer capacity. The amount of acid or base that must be added to the buffer to produce a unit change of pH. That's known as buffer capacity. They denoted as beta equal to equation derivative of concentration of base divided by derivative of pH. That's known as buffer capacity. Derivative of base divided by derivative of pH. That's known as buffer capacity. The buffer capacity always positive value. Since the addition of base, they increase the pH. When addition of base, they increase the pH. When the addition of acid, they decrease the pH. When addition of acid, they decrease the pH. The value of beta depend not only on the nature of the buffer, they also depend on the pH. The value of beta not only on the value of beta depends not only on the nature of the buffer, they also depend on the pH, which is determined by relative concentration of acid and its conjugated base. It is determined by relative concentration of acid and its conjugated base. This is the buffer capacity. The amount of acid or base that must be added to the buffer to produce a unit change of pH. That is known as buffer capacity. A unit change of pH. That's known as buffer capacity. They are denoted as beta. The equation, the beta equal to derivative of concentration of base divided by derivative of pH. Next topic, buffer equation. Buffer equations are also known as Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. First, we are discuss about the for acid buffer. For acid buffers, the pH of acid buffer can be calculated from the dissociation constant Ka of weak acid. The pH of acid buffer can be calculated from the dissociation constant Ko of the weak acid and the concentration of acid and salt used. The dissociation expression of weak acid can be represented as HA. They dissociate from H plus A minus. HA is acid. They dissociated from H plus A minus. The dissociation constant K is the dissociation constant. K is the dissociation constant equal to concentration of H plus into concentration of A minus divided by concentration of HA. That is the dissociation constant. It is the concentration of product divided by concentration of reactant. HA they dissociated from H plus A minus. The dissociation constant represented as Ka, that is equal to concentration of H plus into concentration of A minus divided by concentration of acid HA, or concentration of H plus, when concentration of H plus, that is equal to Ka into concentration of base, concentration of HA acid divided by concentration of A minus, it's salt, concentration of A minus. You understand? The concentration of H plus, that is equal to Ka, dissociation constants, into concentration of HA acid divided by concentration of A minus, that is salt. A weak acid is only slightly dissociated. Weak acid is only slightly dissociated, and its dissociation is further depressed by addition of salt, Xa. The dissociation is further depressed by addition of salt, which is provided by iron. As a result, the equilibrium concentration of unionized acid is nearly equal to initial concentration of acid. The equilibrium concentration of A minus is assumed to be equal to initial concentration of the salt is added, since it is completely dissociated. Therefore, the above equation 1, this is the equation 1. We represent concentration of A minus by salt concentration. This concentration of A minus by salt concentration, that is H plus concentration of H plus equal to Ka, dissociation constant, into acid divided by salt. When equation, this is the equation 1. Equation 1. Ha, acid, concentration of H plus equal to Ka, dissociation constant, into concentration of Ha. Ha is the acid divided by concentration of A minus. A minus, that is concentration of salt. So concentration of salt, that is equal to a concentration of H plus is equal to Ka, dissociation constant, into acid divided concentration of acid divided by concentration of salt. Taking log on both sides, therefore get equation get log H plus plus log H plus log H plus equal to log Ka plus, when Ka into concentration of acid divided by salt. When apply log, they get positive charge, plus into they get plus charge. Therefore, log Ka plus log concentration of acid divided by concentration of salt. Understand? Taking log on both sides, log concentration of H plus equal to log Ka plus log acid divided by concentration of acid divided by concentration of salt. Multiplying both sides by negative signs, multiplying both sides negative sign, they get negative log concentration of H plus equal to negative log Ka minus negative log concentration of acid divided by concentration of salt. Therefore, negative logarithm of H plus equal to pH. You already know the negative pH is a negative logarithm of H plus and concentration, and negative log Ka is the denoted as pKa. Negative log Ka is denoted as equal to pKa. Therefore, equation is changed as pH equal to pKa minus negative logarithm of acid divided by negative logarithm of concentration of acid divided by concentration of salt. Therefore, the equation pH equal to pKa plus log concentration of salt divided by concentration of acid. When negative sign changed to plus, the equation salt, the concentration of salt get above the equation. The pH equal to, the equation is this is the important equation. The pH equal to pKa, plus log concentration of salt divided by concentration of acid. That is the Henderson-Hasselbalch equation. It's a very important equation, Henderson-Hasselbalch equation. pH equal to pKa plus log concentration of salt divided by acid. Equation 3 is called Henderson-Hasselbalch equation. It is helped to calculate the pH value of buffer solution if the concentration of acid as well as the salt are known. The concentration of acid as well as salt are known. They calculating the pH value of buffer. It is used for helping calculating pH value of buffer solution. Next, for basic buffer, buffer equation for basic buffer can be calculated same way as the acidic buffer. They consider a basic buffer composed of mixture of weak base BOH and its salt Ba. The dissociation constant BOH, they dissociate from B plus OH minus. Therefore, Kb equal to is a dissociation constant of base, weak base, that is equal to concentration of B plus into concentration of OH minus divided by concentration of BOH, or OH, concentration of OH minus equal to Kb into concentration of BOH divided by concentration of B plus. That is equation 1. It's same as acidic buffer. Buffer equation for the basic buffer can be calculated same way as the acidic buffers. Therefore, a weak base is only slightly dissociated, and its dissociation is further depressed by addition of salt Ba, which provides B plus ion. As a result, equilibrium of concentration is unionized is nearly equal to the initial concentration of base. Therefore, the equilibrium concentration of B plus is assumed to be equal to the initial concentration of salt, and since completely is dissociated. Therefore, the equation 1 represents the concentration of B plus by salt concentration. Equation 1 is represented the concentration of B plus by salt concentration, that is OH, concentration of OH minus equal to Kb, dissociation concentration of base into concentration of base divided by concentration of salt. Taking log on both sides, therefore they get log concentration of OH minus ion equal to log Kb plus log base concentration of base divided by salt. Multiplying both sides by negative sign, they get negative logarithm of OH minus ions equal to negative log B minus negative log concentration of base divided by concentration of salt. When negative logarithm of OH minus ion, that is equal to POH, negative logarithm of OH minus concentration, negative logarithm of H plus ion concentration, that is pH, but is in case of negative logarithm of OH minus ion concentration equal to POH, and also negative log Kb equal to pKb. Therefore, the POH equal to pKb minus POH equal to pKb. POH equal to pKb minus negative logarithm of base divided by negative logarithm of concentration of base divided by negative logarithm of salt. Therefore, the POH equal to pKb plus negative plus logarithm of concentration of salt divided by concentration of base. That is the final equation. POH equal to pKb plus log concentration of salt divided by concentration of base. It is the final equation. Next, application of buffers. Applications of buffers. First, in biological system, the pH of the blood is maintained at above 7.4 by 2 buffer system. The pH of blood is maintained at about 7.4 by 2 buffer system, that are primary buffers. These are present in plasma. Primary buffer, these are present in plasma. The plasma containing carbonic acid or carbonate, and acid and alkali sodium salt of phosphoric acid. Carbonic acid or carbonate and acid or alkali sodium salt of phosphoric acid. That is the primary buffers present in the biological system. In blood, the pH of the blood is maintained as 7.4. That is the pH of blood by 2 buffer system. primary buffer and a secondary buffer. The primary buffer, these are present in plasma, that's containing carbonic acid and carbonic acid or carbonate and acid or alkali, sodium salt of phosphoric acid. Next, secondary buffer, these are present in erythrocyte. Erythrocyte is RBC. That's oxyhemoglobin and or hemoglobin and acid or alkali potassium salt of phosphoric acid. Oxyhemoglobin or hemoglobin and acid or alkali potassium salt of phosphoric acid. These are two buffer, primary and secondary buffer, present in our biological system, that is blood. Next, in pharmaceutical system, the buffer are widely used in the field of pharmacy as ingredient in most of the pharmaceutical formulation in order to adjust the pH of the product that required for the maximum stability. In pharmaceutical system, the buffers are widely used in the pharmacy as ingredient is most of the pharmaceutical formulation in order to adjust the pH of product that required for maximum stability. In parenteral preparation, next, in parenteral preparation, that is injections. In case of parenteral preparation, pH should be considered carefully as large deviation of pH may lead to serious consequences. When pH increase, that causes serious consequence in our body. Therefore, the ideal pH of the parenteral product is 7.4. 7.4, that's same as blood, which is pH of blood. The most commonly used buffers in parenteral product injections are acetate, phosphate, citrate and glutamate buffer system. The pH of product is same as pH of blood. The pH of the parenteral preparation is also same as pH of blood. When increase or decrease that pH, they cause the serious consequence our body. Some irritations will be occur in our body. Therefore, the pH should be the same as pH of blood. The commonly used buffers in parenteral product injections are acetate, phosphate, citrate and glutamate. Next, in ophthalmic preparation, that is a eye preparation. Ophthalmic preparation is also known as eye preparations. Buffers generally used in ophthalmic preparations to maintain the pH, physiological pH range. Lacrimal fluid, that is eye fluid. The lacrimal fluid, that pH range is 7 to 8, but it has good buffering capacity and can tolerate the preparation having the pH value between 3.5 and 10.5. The lacrimal fluid that have pH 7 to 8, they range 7 to 8, but it's a good buffering capacity and they can tolerate the preparation having the pH value between 3.5 and 10.5 with little discomfort. The outside the range of 3.5 to 10.5. When outside the range of 3.5 to 10.5, they increase the lacrimation may occur with the other complication. When outside the value of the 3.5 to 10.5, they increase the lacrimation may they leads to other complication. You understand? About the pH of the ophthalmic preparation should be the ranges from 3.5 to 10.5. The buffering agent most commonly used in ophthalmic preparation is the borate, carbamate and phosphates buffer system is used in ophthalmic preparation. Borate, carbonate and phosphate. Next, in ointment and cream, the topical product, that is in ointment, the topical products, the example of topical product, that's ointment and cream, which are used to skin. Topical products which are used on skin, such as ointment and cream, are also buffered to ensure the stability of the formulation. They also buffered to ensure the stability of the formulation. The most commonly used in the buffer in ointment and creams are citric acid and its salt, phosphoric acid and its salt. The most commonly used in buffer in ointment and creams are citric acid or citric acid and its salt, phosphoric acid and its salt. So, pharmaceutical applications of buffers. Okay, thank you guys.